if I want to say y is equal to h of x, keep in mind that x is equal to f of t. So we could just replace x with f of t, which is why we get h of f of t. But then we recognize that y is g of t, which means we could replace y with g of t, which is why we now get g of t equals h of f of t. Now, our whole purpose of this is to be able to find a derivative. So that means that why don't we go ahead and do implicit differentiation here? So we have g of t has a derivative of g prime. H of f of t has a derivative of h prime of f of t times the derivative of f of t, which is helpful because notice that that's the chain rule. Notice, though, that if I was originally trying to find the derivative of y, which is h of x, then I was really trying to find h prime of x, which means we should isolate h prime by dividing both sides by f prime. So it looks like all we're doing here is taking g prime of t, dividing by f prime of t, and that is the derivative of that function, that parametric set of equations. But it shouldn't be too surprising, really, because if you think about this, then notice that if I wanted to find the derivative of y with respect to x, then really I'm just taking the derivative of g divided by the derivative of f. But that's not surprising because g stands for y and f stands for x. So I'm just taking the derivative of y with respect to t divided by the derivative of x with respect to t. So if all I wanted to do was find dy dx, but all I was given is dy dt and dx dt, then why don't we take that dy dx, and whatever I do to the top, I could do the same thing to the bottom. So let's divide this by dt. Let's divide that by dt. And now notice that that's how I could find the derivative. Just take the derivative of y divided by the derivative of x. Cool? So that's it. All right, well, let's go ahead and go back to our example then. Okay, this example we had back here, if we want to find the derivative of this set of parametric curves, okay, then I could go back down here and just say, let's find dy dx. All right, well, we're told that in order to find dy dx, all we need to do is find the derivative of y with respect to t and divide by the derivative of x with respect to t. But this one is super simple because notice that y is t squared plus 3, so dy dt is just 2t. dx dt is just the derivative of t plus 2, which is 1. So dy dx is 2 times the t value. So what does that tell me? It tells me that the slope is nothing more than twice what the t value is. So if I wanted to find the slope at this location right here at t equals 1, the slope is just 2 times 1, or 2. If I wanted to find the slope way back here, the slope is just 2 times what the t coordinate is, which is -4. So the derivative is telling me how steep the curve is at each t value, which would also make sense as to why the slope here is equal to 0, because 2 times 0 is in fact 0. Any issues with that? Okay. Well, you should be able to find horizontal and vertical tangents as well, and I won't go a whole lot into that, but think about when vertical tangent lines occur. How do I get horizontal and vertical tangent lines?
Horizontal, you get that when the numerator is equal to 0.
Yeah, or not only just when the numerator is equal to 0, but you get horizontal tangents when the derivative is equal to 0. Now, if you have a fraction, then that means that it's where the numerator is 0. But in general, if you don't have a fraction, it's just where does dy dx equal 0? Right? What about vertical tangents? How do we find where vertical tangents are?
When dx over dt does not equal 0?
Okay, so again, going back to this form right here, because it's a fraction, you're basically saying where is the denominator not 0? Or where is it 0, which would tell me the vertical tangent lines. But in general, you might not have a fraction. So in general, what we're doing is we're just finding out when is dy dx undefined. All right, so we're finding when dy dx is undefined. But let's think about it in terms of this fraction. And now, as Sophia was noticing, dy dx is equal to 0 when the numerator is 0. So I know that this is actually going to happen when dy dt equals 0. And I know dy dx is undefined because I know that this is always going to be a fraction of dy dt over dx dt. I know that dy dx will be undefined when the denominator is 0. So vertical tangent lines are when dx dt is equal to 0. That seems pretty reasonable. Okay. All right, well, sometimes we want to find the second derivative as well. The second derivative is actually a bit more complex, okay? So one thing you can do is just eliminate the parameter and then differentiate twice. But again, that doesn't help us because a lot of times we want to be able to look at it and look at the concavity in terms of t, not in terms of x or y. So,
Professor,
yeah,
how about dy dt and dx dt equals 0 in the same time?
Say that one more time.
Dy dt and dx dt equal to 0 in the same time.
Oh, if they're equal to, that's a good question. If they're equal to 0 at the same time, then it's still going to be undefined. It's just that that's indeterminate form. So the 0 in the denominator overpowers the 0 in the numerator. So essentially, when I say 0 over 0, that's still undefined. Okay. The only difference is that there might be a situation where if dy dt, let's see, if dy dt is equal to 0 and dx dt is equal to 0, then that means they have a common factor which can cancel out, which may indicate that there's a hole, and therefore it wouldn't be defined in the first place.
Would you have to incorporate L'Hopital's rule in that situation?
No, because L'Hopital's rule is for finding limits, not for calculating the derivative of each. Typically, it would be, normally that would happen, I think, when you have common factors between dy dt and dx dt. And if you do, then I feel that that would mean that there is a removable discontinuity. So I'm guessing that that would mean that there would be a hole if that was the case. Either way, though, it would mean that the derivative is undefined. Okay, so anytime dx dt is equal to 0, it's undefined. They just may not always be vertical tangents if that function is undefined at that t value. Okay. All right. Well, let's take a look at this next component here, trying to find dy dx. Okay. So, or the second derivative of y with respect to x. So keep in mind what d squared y dx squared means. And again, this is notationally very important for Calculus 3. When you look at this notation, look at what that's actually referring to. It's telling me to take d dx of the derivative that I already have. D dx is the operator that says to take the derivative of dy dx, which is already the derivative. And so look at why Leibniz ended up, kind of coming up with this notation where you put the little 2 up above the d here, and then the 2 up above the dx over here. That's because if you look up top, there are 2 d's. And if you look on the bottom, there's 2 dx's. Which is why we write it as d squared y over dx squared. Okay? So we're trying to find the second derivative. So notice with dy dx, we wouldn't really have dy dx in terms of x, so that's why we would have a dy dt over dx dt. But again, derivative operators actually work very similar to fractions, to where this is kind of like d dx over 1. So I'm taking the derivative of this function, but if I think about it just in terms of the operators, that would mean that I could put the d dx up top, right? So I have d dx of dy dt over dx dt. But again, if these operators are working just like algebra, then dx and dt are interchangeable. So I could actually just move those around, and I could say, you know what, d dx of dy dt is the same as d dt of dy dx, which is actually really helpful because dy dx is already in terms of t. So if I now say d dt of something that's already in terms of t, then I just differentiate that new derivative like normal. So the derivative of dy dx is going to be the derivative of dy dx with respect to t divided by the extra derivative of dx dt. And that is one proof of why that works. There's another proof of why this works as well. Is that, let's just do the quotient rule here. Let's do this again. Let's say that we want to find, d dx of dy dt over dx dt. Well, notice we could do the quotient rule. We could start with the bottom. All right, the bottom would give me dx dt. Times the derivative of the top. Well, the derivative of the top is d dx of dy dt. Minus the top, so minus dy dt, times the derivative of the bottom. Well, the derivative of the bottom is d dx of dx dt. Right? And that's all over dx dt, or the bottom, squared. So that's it, but we could actually simplify this a little bit here, okay? If we were to simplify this, then I could recognize a couple of things here, okay? One thing I can recognize is that we're left with, we have this dx dt showing up in multiple parts. So here we have a dx dt, and here we have a dx dt, which means that factor is going to cancel out with one of those dx dt's. So we can now simplify this a little bit more, okay? We first of all get d dx of dy dt. You know what? Before we do that, we're going to look at this a little bit differently. Okay. If I now say, I'm gonna rewrite this piece right here. Okay. So first of all, let's write dx dt And over here, remember, in a very similar way to where we said d dx of dy dt is the same as d dt of dy dx, that's going to be beneficial when we end up looking at this piece right down here. This piece right here. Because d dx of dy dt is the same thing as just flipping these two denominators here. So we could rewrite that as d dt, write that as d dt of dy dx. Which is helpful because now dy dx is already in terms of t. And finally, we got minus dy dt times, and over here, d dx of dx dt is the same as d dt of dx dx. What is dx dx though? What does dx mean? What does dx dx mean?
So this term is 1?
It's just 1 for a couple of reasons, because dx dx is the same quantity on top and bottom, so that cancels. Dx dx is also the same thing as d dx of x, and the derivative of x with respect to x is just 1. So what is d dt of 1?
0?
0. So doesn't that whole piece go to 0? Which means this entire piece goes to 0? Which means that I need a little more space. Okay. Which means that if that whole quantity went to 0, now all I'm left with is this. And now notice that there's a dx dt in top and bottom that can cancel, which now tells you that d dx, or I guess we could write it as d2y dx squared, is simply going to be equal to the derivative of dy dx with respect to t divided by dx dt squared. Not squared. And there's that. So you get the same answer either way. Okay. It's just that, you know, this is one way to do it. There's two different proofs to get to the same exact place. All right. Any questions there?
Maybe I was reading too much into it, but before you rewrote this equation on the right there, it looked like we were very close to getting the numerator equal to 0. That's when you decided to rewrite the stuff that we have like in orange on the right.
Well, we weren't going to get the, we could have done this a little differently. We could have canceled that out. The problem is that we would have canceled, okay, put it this way. Let's say that this canceled out with one of these. That's okay, because that still would have been a 1 here. So d dx of 1 would have been 0 still anyway. Okay, so I could have gone, I mean, I could have done this a little differently. I could have gone back to here, and I could have canceled out dx dt from here, and dx dt from here, and a dx dt from here. And all that would have been left would be d dx of 1. D dx of 1 is still 0, so that would still cancel that entire quantity, and therefore I still get what remains.
Okay. I get it.
Right? It's just that oftentimes we're not used to dealing with derivatives and differentials in this particular way. But this is actually how in Calculus 3 we really notationally deal a lot with dy dx's, with ddt's, with dt's, with dy's, with dx's. So we deal with all of those. And so this is basically what we're kind of doing. All right. One last thing that I want to do is before doing an example, why don't we find out how to do an arc length? Okay. So we could actually do area and arc length in a very similar way. Okay. So remember that with parametric curves, you're going to be given two separate parametric equations, one describing y and one describing x, right? But if I want to find the area underneath a curve called y equals f of x, I don't actually have that function. But if I did have that function, I would simply be taking the integral of f of x dx. But I don't have f of x dx. So what we would do at first is we would recognize that y is actually our function of x. So that means that this quantity right here could be replaced with y. So instead of f of x, just replace it with y. And so now what I'm doing is really saying, let's integrate y dx. Let's integrate y dx. Well, if I integrate y dx, then that just means that I got to go to my parametric equations and recognize that y is actually g of t. So that's g of t. And then dx is nothing more than the derivative of x. Dx is equal to f prime of t dt, which is why I'm multiplying by f prime of t dt. And now I've just got to realize that in order to find the area using parametric curves without having to eliminate the parameter, all I have to do is take the y function and multiply by the derivative of the x function. And notice that my alpha and beta have changed as well, because I'm basically going to say, well, if I'm given x equals a and x equals b, I got to find the corresponding t values. So that's why I'm going to convert these to alphas and betas, where t is equal to alpha and t is equal to beta. Okay, so you can see that we're deriving all of these formulas in this f of t dt. We're deriving all of these formulas, but once you have the formulas, now we just have a few ways to actually compute these. Okay, so this tells us in this case that area could be found by evaluating this function or this integral, right? We're able to compute the derivative of a function by simply applying this formula. We're able to use the second, or find the second derivative of a function using this formula. So essentially, we're deriving all of these formulas, but once you have them, now it's just a matter of applying them. All right, so let's take a look at arc length then. So arc length is really similar. Remember that we've got our standard arc length formula, right? But now we can't deal with dy's and dx's because we have dt's now. We should have everything in terms of t. So what our job is to just change dy dx and dx separately into t's. Well, dy dx is pretty easy because we know that that's the formula for dy dt over dx dt. And I could actually replace dx pretty easily by just multiplying by dt over dt. So this right here is equivalent to dx. So look at what we can kind of do at this point. We could get a common denominator to be able to merge 1 plus that quantity squared. So we just got a common denominator, which allowed me to compare these into 1 right here, right? But notice if I take the square root of top and bottom, notice the square root of the denominator is just going to be dx dt. So that's going to tell me that this whole square root of dx dt squared is going to cancel with that dx dt. And so the formula parametrically to find arc length is just to take the derivative of x with respect to t squared plus the derivative of y with respect to t squared, and then take the square root. This actually has a really simple reason as well, geometrically. And that's because if I have some curve here, okay, let's call that function f of x. But I know that it's also defined parametrically to where there's actual t values that are moving along here. Okay. Then essentially, let's look at what this length is going to be. Okay. This length right here is one tiny little arc length. Now, if I were to recognize this in terms of a triangle, okay, then this would be our small change in x, and this would be our small change in y, right? But notice that that would imply that this length right over here is going to be, by the Pythagorean theorem, the square root of dx squared plus dy squared. But notice that if we were putting this in terms of t values, right, and let's just say that this is from t equals alpha to t equals beta, then I could actually just make these proportional by dividing each of these by dt, so that now this is the derivative of x with respect to t and the derivative of y with respect to t. So now notice that all I have to do in order to find that arc length is take the square root of dx dt squared plus dy dt squared from t equals alpha to t equals beta, and I end up adding all of those tiny little line segments that are going to be moving along here. And that is kind of a more geometric representation of why this ends up working. Okay. So we've got all of these different formulas now in terms of parametric curves. Basically, what we're able to do at this point is just use all these formulas. It helps to understand their derivation in case you forget these formulas. But these are all the formulas we need, and now we can actually do a little bit of work here. So I'd like to just finish up one of these problems here and share with you an example. And so let's just take a look at this example and see how it asks us all kinds of interesting questions about tangent lines. Notice it's not asking me anything about eliminating a parameter. It's just giving me two different parametric curves. X is equal to t squared. Y is equal to t cubed minus 3t. And I don't need to find the function y equals f of x in order to convert this, right? So all I want to do is maybe answer a few of these questions. It says, show that C has two tangents at xy equals 3, 0. Okay, well, that's kind of an interesting question. So basically, we're saying that if we have some curve, and I don't know what this curve looks like, but the beauty of parametric curves is that they don't have to be functions, right? I could just have any random curve like this one right here, right? And that's a curve defined parametrically. So if I were to look at a particular point, maybe this point right here, look at how that's a point where two of those graphs cross. If you look in one direction, notice how the tangent line is like this. But on the trip around the first place, the tangent line was like this. It's possible to have two different tangent lines at the same place if you have graphs that are crossing. So the first thing to recognize here is that, that you were told that 3 was the x-coordinate and 0 was the y-coordinate. So look at how we could actually just plug in 3 for x and 2 for y, or 0 for y, and see that that's going to happen when t is equal to plus or minus root 3. That's already two locations. And then I could see that if t is equal to 0 and I factor, that I also get another location. So it looks like there are two different t values where the x-coordinate is 3, and there are 3 different t values where the y-coordinate is 0. So I could see that the graph crosses where they intersect, and that's at plus or minus root 3. And so those are two different locations. So that's something similar there. All right, but then it says find their equations. So why don't we find their equations by just taking dy dx? Notice that that's pretty straightforward. If I want to find the slope of dy dx, I just take the derivative of y with respect to t and divide by the derivative of x with respect to t. And so if I wanted to find the slopes at those t values, we're just plugging in negative root 3 and positive root 3 to our derivative. So when I simplify, I find out that at negative root 3, the slope is also negative root 3. And at positive root 3, the slope is also positive root 3. Total coincidence, by the way. Don't think that that's always true. This was just a total coincidence that you looked at the t value of negative root 3, and the slope just happened to be the same. You look at a t value of root 3, and the slope just happened to be the same. So if I wanted to find the equations of tangent lines, just keep in mind that that's y minus y1 equals m times x minus x1. And so notice we just came up with our two equations. So a lot of this is going back to the work that we did in Calculus 1. Right? In Calculus 1, we did a lot of work with derivatives, a lot of work with tangent lines, a lot of work with finding points where tangent lines were certain slopes. And now we're revisiting that, but from a different perspective, because now we can actually use curves defined parametrically in order to, find all the information we need. All right, this next one says find the points on C where the tangent lines are vertical and horizontal. Well, this is our derivative. Right? Here's our derivative right here. And we mentioned earlier that derivatives slopes are horizontal when the numerator is 0, and slopes are vertical when the denominator is 0. So we're just setting the denominator equal to 0 to see that that's going to happen when t is 0. And setting the numerator equal to 0 and factoring, we get that that's going to be at t equals plus or minus 1. So since I know that the t value dictates what x and y will be separately, right, from up here, the original values, x and y are dependent on t. If I know what the t values are, I can find those corresponding points. So that allows me to then tell me that these are the particular locations. Cool. How do I know where the graph is concave up? Well, we know it's concave up or down when the second derivative is positive or negative. So let's go back to that formula. Remember that formula said, let's take the derivative of the derivative and then divide by an extra dx dt. So this is where we now just are simplifying to get our derivative, and I'll let you go through the process of differentiating. But when you differentiate and simplify, this right here becomes the second derivative. Notice again, the second derivative is in terms of t, just like it should be, right? Because notice that the parametric equations were in terms of t, so our second derivative should be in terms of t, right? So if I want to find the points of inflection for this, where the graph changes concavity, we just got to find out where is the numerator equal to 0, which it never is, and where is the denominator equal to 0. So notice our only point of inflection is at t equals 0, so if I put that on a number line, then I could determine the values that are negative are going to cause this second derivative to be negative, and values that are positive will cause the second derivative to be positive. So again, just like from Calc 1, all we're doing in order to determine concavity is look at the points of inflection and then see whether that second derivative is positive or negative. Okay, wherever it's positive is concave up, so it's concave up when t is greater than 0 and concave down when t is less than 0. So look at my point of this. The point is, even though we don't know what this graph looks like, we can already start to interpret a few things that we know about this. Okay, I know a couple of things here. I know that there is a point of inflection, and the only point of inflection is going to occur at t equals 0. I also know that there's a vertical tangent line at 0, 0. I also know there's horizontal tangent lines at 1, 2, and at 1, negative 2. So I'm just going to go ahead and try to graph this because we've got all the information we probably need. Okay. So let's try that. Okay.
For the exam, are we going to have to determine concavity?
I will ask you to find the second derivative in order to, yeah, probably going to have to find concavity. Potentially points of inflection, you'll definitely have to know how to find second derivative. I don't recall exactly if I asked you to determine concavity or if I just asked you to find the second derivative. I think I only asked you to find the second derivative, if I remember right. Okay. Well, okay. So let's take a look at a few things. It said, first of all, that there is a vertical tangent line at 0, 0. So why don't we plot our 0, 0? Because 0, 0 must be one of our points on the graph. Okay. It also told me a couple other points on the graph that there were horizontal tangent lines. Okay. Okay, so I can see first of all that that when I square all of the t values, I get x is going to be positive. Okay. If I look at this, this looks like it is 1, 2, and then 1, negative 2. So if I plug in 1, 2, 1, 2 would be right here. One negative 2 would be down here. Well, now I can see automatically that this is definitely not a function, or rather not a function of x. It could be y, x as a function of y. Okay, and I should be able to also recognize that these have some corresponding slopes from the information we found. We found that this should be vertical by the time it passes through here. It should be horizontal by the time it passes through here. Horizontal by the time it passes through here. And we also see something else, because this occurred right here when t was equal to 0. This occurred over here when t was equal to 1. Okay, and this occurred down here when t was equal to negative 1. Okay. Everybody okay with that? Or is that right? So when I plugged in 1, I got negative 2. So this was actually the opposite. Okay. So I went back to find my y coordinates, and it turned out that this was t equals 1 and this was t equals negative 1. Cool. So we got some information about that. I still can't quite tell what the graph is going to look like, but that's why we ended up looking at some points of inflection as well. I see that there's, when t is greater than 0, the graph is concave up. Okay. When t is less than 0, the graph is concave down. Okay. Well, that's kind of interesting, because that tells me that when t is negative, meaning in this range over here, it's going to be concave down. So that must mean that it's going to look something like this. Concave down, right? Until it reaches a horizontal tangent. And then it looks like it's going to be concave up when it comes down here. Now, it's kind of tough to tell what ends up happening beyond this. I don't know. I feel like I would need some more information, because if it was concave down the whole way, then that would mean that it would have to come back down and around here or something, which implies to me that there would have to be another vertical tangent line, but there's not. So it's kind of tough to tell what's actually going on past -1, but that's not really our point. The point is that I wasn't even planning on graphing this, but I was recognizing that, you know, with all of this information that we could create, we could find what these values actually are. Okay. In fact, it's possible that this now that I'm looking at it, when t is √3, the slope is √3. So that means that by the time I continue t equals 0 to t equals 1, I could continue to increase like this. And then when I continue to decrease, because it has to be concave down the rest of the way, then it looks like this is probably going to be something like this. These are going to give me positive t values of, say, √3, while these give me negative root value or t values of, say, negative √3. So there's all kinds of stuff that we can interpret. I don't know what this graph actually does look like, but that's
Professor.
yeah.
The problem did say like the graph past 3, 0.
It said what?
Past 3, 0.
It said that at 3, 0. Oh yeah, there were 2 tangents at 3, 0, which is why. Oh, so thank you. We just used some more information there. Thank you. I forgot about that first part. It said that at 3, 0, there were 2 tangents. Right? Which means that if I go to right here at 3, 0, 3, 0 is right here. That tells me that there is, in fact, another point, but to have 2 tangents means that it crosses. So that must mean that this right here is going to cross at 3, 0, while this right here is also going to cross at 3, 0. And sure enough, from that information, we were able to actually come up with a potential value, which means that this location right here, it's got a t value of √3, but also a t value of negative √3. So if we were to draw this as a plane curve, we could see that it is going in this direction in the negatives, right? And it's coming around here, hitting t equals 0, and coming around t equals 1, and it continues to go off to infinity. Right on. So just based off of all the information that we ended up creating here, we just plotted all the information that we had and found out that these were the important points where interesting things were happening.